So today we have Dr. Maddie Smith, who's an assistant scientist in the Applied Ocean Physics and Engineering Department at WHOI. Motivated by the loss of sea ice in a rapidly changing climate, her research uses observations and modeling approaches to understand how sea ice interacts with the ocean. Her fieldwork has taken her to the oceans at both ends of the Earth, including participation in the summer leg of the year-long Mosaic expedition to the Arctic. Maddie completed her PhD in civil and environmental engineering at the University of Washington. So please join me in welcoming Maddie.
Thanks so much for the intro, and thank you all for having me here today. It's really fun to be here. So I've been down the road at Woods Hole Oceanographic Institution for just over a year, but I started my career in oceanography just up the road at Bowdoin in Maine, studying the coastline of this region, which is where I really fell in love with studying ocean processes and surface waves. So since then I've mostly been working in the ice-covered regions. Sometimes I joke that I'm more of a solid-state oceanographer now because I work a lot with ice. But I've been more and more thinking again about coastlines, both in the Arctic and more locally. So I'm excited to talk to you about some of that work today. In particular, focusing in the meat of this talk on a really new, exciting observational method for using seafloor cables to measure surface waves and potentially a lot of other processes and properties in the coastal ocean. I think this will be very useful for environments like the Arctic, but also environments that are closer to home. This is work that's in collaboration with a lot of people. Notably, a lot of the Arctic work is with the people on the top line here, and then the bottom line is collaborators that I've been working with at WHOI for some of the more local work. Okay, so what sets the Arctic coastline apart from the rest of coastlines is largely the presence of seasonal sea ice, or at least from my perspective as a sea ice scientist, that's what's really unique about it. So this is a series of worldview or optical satellite imagery from the coastline of the Alaskan Arctic. So the northernmost point in the US is right here. And you can see this is the evolution, the seasonal evolution through the sunlit season. And so you can see, open water season in the middle of the summer, and then when we have this ice cover throughout the winter, that basically acts like this extension of the coastline, for much of the winter, kind of continuously covering the coastline near the land. So I think motivating understanding coastlines is probably already pretty well motivated for this group, but the motivations are largely hold within the Arctic as well. There's a lot of change happening across the Arctic, but also Arctic coastlines. And the importance for coastal communities is true there as well. Across the world's coastlines, communities are concentrated along those regions. In the Arctic, I think it can be argued that all of the communities there live along the coastline. So these changes that we're seeing with eroding coastlines, loss of sea ice, creating more surface waves, impacting coastal ecosystems, and thaw of the coast that's contributing to damage to infrastructure is especially important for these remote communities that are very dependent on these coastal ecosystems. Part of the system is the landfast ice that we saw on the first slide, which is really, it's called landfast ice because it becomes grounded on the shallow seafloor near the coast. And so it acts like an extension of the coastline because it stays there for many months throughout the winter, depending on where we are. And so this acts as a really important interface for ecosystems, but also the local communities to travel and hunt throughout the winter. So you can see some people on the snow machines probably going out to hunt in this image. This is separated from the drifting or pack ice offshore by flaw leads, which you can see in the schematic. You can also see a flaw lead in the back of this image. And so that's what really sets apart this landfast ice that we're focused on from right near the coastline from the kind of more classic ice, which is really dynamic and moving and has some differences in the seasonal cycle. Like the sea ice in general, landfast sea ice is really rapidly declining with the changes that we're observing in our climate and the amplified changes in the Arctic. And with this, we're seeing when landfast ice is not present, we have more time where wave activity can contribute to coastal erosion processes. Some of this is similar to like we have in any coastline around the world, but also there's some aspects of this that are unique in the Arctic where we have permafrost coastlines which can undergo these really rapid erosion events, such as thaw slump, which you can see in the photo here, where there's just these large areas that erode very rapidly with coastal cliff collapse as well. Part of the reason that these processes are becoming more accelerated is because of the change in ice covered area, which is changing the oceanography of the Arctic Ocean. And for my interests in particular, we are seeing much larger areas of open water that are driving more significant wave activity. So just kind of anecdotally, if we look at maps of the satellite sea ice extent from 1979, 2012, we can see much larger open waters area in 2012 and also in recent years, where we can imagine wind blowing over is going to create much bigger waves. This has been shown also with observations looking over time. We can see dramatic increases in the average wave height over this area north of Alaska, where the wind speed is staying about constant. So this increase in wave height and wave energy is really coming from this increase in fetch over the basin in general. So this is looking at the waves that are forming in the open water. And then of course, these waves are propagating both into the pack ice offshore and then into the ice near the coastline in the winter. Yeah, and so this, I think it's helpful to then think about what waves and ice look like and what those interactions, the myriad of interactions that are happening within that region. So this is a video just showing an example of what that looks like in new sea ice that's forming. And I think it's I think it's beautiful to watch waves in sea ice. I mean, this is part of what captured me working in this field. But you can really see here a lot of the processes that are at play where we have rapid attenuation of the waves, but especially the high frequencies. These waves are really different than waves that you see in open water, because a lot of that high frequency energy is really attenuated primarily through dissipation in this type of new sea ice covered. You could hear that it was windy, so it's not that it wasn't windy. There was still plenty of wind energy, and yet the surface was very smooth. So we can see that type of signal in observations too, in the landfast ice region near the coastline, where that type of ice and its persistence throughout much of the year limits the wave exposure at the coastline. So this figure is comparing observations from 2 moorings, one, the blue one that was within the landfast ice zone, and then the gray one is in the offshore of the landfast ice and primarily open water. And so looking at the wave heights on the top, you can see there's this large period of time where there's no wave energy in the landfast ice, but there's plenty in the offshore buoy. And then even through the spring, once there starts to be more wave activity propagating into that landfast ice, but that is still being attenuated by it. And so what this means over time is that we end up with much less cumulative wave exposure at the coastline. That is, so providing protection for the coast. Yeah, so that cumulative wave exposure is reduced by the presence of landfast ice. As I mentioned already, the length of time when landfast ice is absent along the coast is increasing in the warming Arctic. So these plots show from reanalysis data the days of open water and the coastal wave exposure from 1980 to 2020. And you can see that those have increased over time. This raw product from AIR5 reanalysis is not accounting for the landfast ice of the coastline though. When we then include that an adjustment for the presence of landfast ice, which is now shown in teal, we really reduce that slope in the change in open water days and the coastal wave exposure. And what that suggests to me is that the role of landfast ice protection is becoming even more important with this rapid change in landfast ice. So not surprisingly, this results in the coastline being exposed to open water conditions for longer periods. And a lot of this is also coinciding with the times when there's fall storms. And so as a result, we can see a lot of hotspots of erosion along the Alaskan coastline. So in this map, you can see areas of red indicating really particularly high erosion rates, some of the highest around the world. But even most of this coastline is at least in the yellow. So positive erosion rates along much of the coastline. However, understanding of the processes by which waves are breaking up the coastal ice and contributing to this coastal erosion are still limited, and that's largely because of the sparsity of observations in this area, which is remote, really hard to measure because of all these dynamic processes that are occurring. So one big aspect of this is that the conventional ways that we measure waves and also waves and ice have trade-offs in the sampling that we can do. So buoys, we often deploy drifting buoys in sea ice covered areas where we can deploy fleets of buoys across a gradient and let them drift to cover, so have some evolution in space over time. But because of their drifting nature, they lack persistence in measuring these gradients. So this is a plot showing where we can combine a bunch of buoys and understand the variation in wave attenuation with distance from the ice edge, but that's just one snapshot in time. The other main way that we would use to look at this traditionally is with moorings, which have persistence over time, but they really lack the spatial resolution. It's hard to deploy enough moorings to get the spatial gradient to understand everything that's happening. So in this time series, you can see two moorings, more inshore and offshore, similar to the figure that we saw earlier. And we're covering the full seasonal cycle of what's happening in this region. But with just these 2 points, there's periods where there's really strong gradients and differences between these two measurements, but we really don't have any understanding of what's happening between those because of the lack of spatial resolution. Okay, so what we propose is a really kind of potentially, groundbreaking and could really change the game in the way that we understand waves and sea ice is using seafloor telecommunication cables to make measurements of waves, which can give us both temporal persistence and also spatial resolution. So the way that we can use cables to make these measurements is by connecting a distributed acoustic sensing called DAS interrogator. So what this interrogator does is that it sends lasers into the fiber optic cable. So if we're using a fiber optic cable that's laying on the seafloor, it's beneath all the surface waves or anything that's happening in the ocean above. It sends a laser into the fiber, which is scattered off impurities in the glass throughout the fiber optic cable, and those are backscattered towards the interrogator. And so what this gives us is it's using that backscatter to measure the strain or strain rate. That depends on the instrument that you're using. And that strain of the fiber along the whole length of the fiber is responding to different acoustic waveforms and also pressure perturbations, such as from surface waves. What's really cool about this method is that we can measure continuously, so we can get high spatial coverage at really high temporal resolution, up to often we record it up to 1 kilohertz. So really high frequencies that you can get a lot of different signals. And also it can have really high spatial resolution. So depending on the instrument, a channel spacing in the range of 2 to 10 meters is common. So you can imagine, you can measure over cables of up to 40 kilometers. So you can imagine with a 40-kilometer cable, 2-meter resolution, that's like having thousands of buoys out along this cable, which is something that we would logistically never do. So with this data, there's potentially a lot more that we can look at. Oh yeah, this is just one more schematic kind of showing to help you get a little bit of a sense of what that looks like. So we would attach the interrogator, the instrument is attached on the shore side of where these cables come up. So often we're using telecommunication cables, so those would go on the seafloor, going out from the coastline and then extending across the ocean to wherever they need to go on the other side. But that seafloor cable is being exposed then to a lot of different acoustic waves and different perturbations in the ocean. And so those backscattered pulses are giving us information about that. Oh yeah, and the other thing that's great is that because these are bringing internet, they often end up, these cables are coming to shore near communities, which are often places that are important for measuring. So there's a good kind of alignment in the places that we want to measure and also where these measurements are already feasible. So the first kind of indication that we could measure waves from seafloor cables, I think this was the first paper showing it, where they were using a data set from California off the coast of Monterey. And a lot of the work using this type of methodology has been focused on like seismics and looking at different seismoacoustic signals. And that was the main approach or kind of goal of this as well. But they realized that there was this large kind of noise in their data set, but also the signal of surface waves. So this is just raw spectra from the strain, and they're comparing that to a nearby wave buoy. And so they saw that a lot of that strain, the energy in the strain signal correlated with the surface waves. And so after this paper, there was a lot of excitement that we could apply this to actually not just like indicate waves are here, but actually in the future to quantify. So a lot of these papers that initially came out were just showing that qualitatively we can see waves. And so now the paper with our recent work, we have some of the first results quantifying waves with this method. So where we were doing this, based on my motivation for this work that I gave already at the beginning, you could guess that we were going to go somewhere where there was sea ice. So we're going back to the Arctic. And so this is a telecommunication cable that comes off the point. So it's part of a network in Alaska on the North Slope. So part of that northern coast. Cables are going into communities to bring internet to them. And so we're using a portion of the cable that goes out from Elliptic Point, which is nearby Prudhoe Bay, which if you've heard of it, it's probably mostly because it's where the oil pipeline starts. There's a lot of drilling activity in the area. And so this fiber, we're using interrogation data from around the first 40 kilometers of that cable. And this is mostly being led by collaborators at Sandia National Labs, who have been collecting all this data to try and understand all the different signals that you can get from these types of measurements. And so we've been working with them, focusing on the surface wave observations and to a degree also the kind of wave conditions, or the sea ice retrievals that you can get. Oh yeah, I also want to mention that this is a relatively shallow shelf for quite a ways out. So you can see, I think out here, this is about 20 meters deep at 40 kilometers offshore. So because it's so shallow for so far, we still see that pressure signal from the surface waves at the seafloor along this full length. So that's what allows us to do this here. So our collaborators have been working on one of the things that they've been measuring is using it to measure the ice at the surface. So based on the fluxual gravity waves through the ice through the winter, so you could remember to that image at the beginning, the ice is covering this area for a lot of the winter with pretty stable ice cover. But there are very low frequency fluxual waves that go through the ice. And so assuming some things about the mechanical properties of the ice, they were able to back out what the thickness of both the ice and the snow are. And so this profile on the right shows that inverted thickness of the ice in yellow and then the snow in red. And from this experiment, initially, so far, we don't yet have in situ data to validate it, which we will hopefully have from this year to do this more qualitatively, to show that the quantitative estimates are accurate in the future. But these thickness values definitely agree with the kind of typical values that we see in this region. So it seems like a very reasonable inversion and has structure similar to what we would expect. So going into the open water season, you can also see throughout a lot of the summer waves on this cable. And so to understand quantitatively what those waves look like along the fiber, we're going to start with the open water season as the easier case. And we're going to use, we used wave buoys, so a very traditional way of measuring waves to both calibrate and then validate those measurements. So here we used one wave buoy. You can see it was moored, so it's anchored along that cable in August of 2022 to coincide with a 1 week of data collection in liquid this. So this figure shows the kind of first results of that empirical calibration and then the comparison of those. So this is a time series, so it's going over the 1 week of data collection. And the orange are the results from the wave buoy. So it's the significant wave height and then their energy weighted period. There's not a lot of dynamic range, unfortunately, over this period, but there's enough to kind of see some signals and whether we can capture them with the DAS data. And so the results from the cable or from the DAS are in purple, and you can see that it captures a lot of the variability over time. It's not perfect. There's definitely some periods where there's room for improvement, but it's capturing a lot of that variability with relatively small errors in the wave heights of 0.1 meter and in the period of just around half a second. Okay, stepping backwards now, the way that we did this was with empirical calibration, where for each channel we took that whole week of data and at each point in time divided the spectra from the buoy by the spectra of the strain from the cable. And so that gives us so this is just that ratio of these two spectra. And so the purple lines are from each point in time over that period. And then the black line is the median of that, which we use as our correction factor to apply to the full data set as a consistent correction factor. So we do this at each point along the cable from 10 kilometers to 35 using our buoys. So there's some assumptions about that the waves are relatively homogeneous in the open water season over a sufficiently long length of time. So that's the assumption that we make for this calibration for this data set. So then from applying this calibration then back to the strain spectra, we can get from the DAS a calibrated wave spectra. So the initial spectra that comes out of that is the dash line. There's some additional QA and QC that we need to do to make a reasonable like physical looking spectra that we can get bulk wave parameters from. So for example, in this one, there is occasionally some high frequency noise, or there's some high frequency peaks, like you can see here. We're actually not sure yet if these are noise or if there's some other physical reason that's driving these peaks in energy. We have a few hypotheses that we're working on testing, but for this purpose, because we don't see this in the surface wave spectra, we apply a cutoff and fit the rest of that spectra with the canonical f to the -4. Okay, so then from that, that's how we get this calibrated DAS wave parameters, which we saw again before, but again here in the purple. So in the open water season, we're assuming that there's less variability along the cables, but this data is still really useful because this is an area of sparse observations. It's really hard to get measurements out. And so having this way to unobtrusively make measurements of the ocean persistently is still really useful. And so an example of where that's true is comparing it to hindcasts of waves for this region, which are shown here in blue. So we don't necessarily expect hindcasts to be good for predicting waves for this region. They lack the necessary resolution to capture those seasonal transitions, especially during ice breakout and ice formation. But because there's a lack of alternative data, they've often been used in this type of analysis to look at coastal wave exposure. And so one way that this data might be useful even during the open water season is to provide just these persistent measurements of wave parameters that we can use for those types of assessments. Okay, but when it gets really interesting is when we have a lot of spatial variability. I argued at the beginning that the thing that makes the Arctic coast most interesting and different is the fact that there's sea ice. And so in this image from November, we can see a lot of that spatial variability. This is a synthetic aperture radar image, so from Sentinel-1. So on the bottom here is the land, so that you can see the outline of the coastline. This is the point where the cable comes out. The white areas are where there's thin new ice. This is November, the ice is just forming. It's kind of like what we saw in that video of the waves on the surface. So we have some new ice forming out along the outer part of the cable, and then also on the inner part near the shore. So this is what will become this thicker landfast ice. But right now it's just forming, and we have also this patch of open water offshore between the two. So we had a week-long DAS experiment during the time when this image was collected. And so we applied the calibrations from open water to this data, and we can get wave parameters from the channels along the cable throughout this time. And we see some really cool things. So what we're looking at in this plot is now not a time series, but it's a spatial slice. So we're looking from 10 kilometers along cable to 25. So it's kind of, if I can point. Anyways, it's kind of along that point from in the ice to out in the open water. And so as we'd expect, we see larger wave heights that are relatively consistent in the open water part. And then those wave heights decline going in through the ice edge and then towards the coastline. And that aligns with, even though these are offset by a few hours, the image and the observations, it does align pretty well with around where we think that ice edge is in the image as well, where we delineate the ice edge in our data, which is indicated by that vertical line. Looking at the wave period, we similarly see what we would expect, where we have over spatially going into the ice an increase in the wave period. So that's associated with the attenuation of the higher frequency waves. So we have shifting of the energy towards the lower frequencies. So this is what we'd expect, but it's still incredibly novel and exciting to see it in such high spatial resolution, as usually we would just have maybe a few points along this transect. But we can also take advantage of the fact that we have these spectral data along this transect, where we have information about the waves as a function of frequency as well, and then compare between two different points. So when we're thinking about wave attenuation in ice, this is the equation that we tend to use to quantify that. So the attenuation can be quantified as a function of frequency. And so in this example, we're calculating that using a comparison of spectra from 2 points, which are indicated by the lines here. And so then if we calculate the attenuation as a function of frequency, we get, this is the kind of shape that we would expect to get where we have higher attenuations at higher frequencies. Okay, so we can look at that for our data. So here we have the wave height attenuation is commonly calculated as well. It's easiest to do with just the bulk wave height parameters, but we can also look at it using the frequency data. So here I've plotted attenuations at 2 frequencies, 0.1 and 0.2. We see what we would expect, that initially the attenuations are higher at the higher frequencies. Interestingly, as we get closer to shoreline and so much of that energy in the higher frequencies has been attenuated, those actually swap. But in general, we see the attenuations increase right when we get near where we delineate the ice edge. And there's some variability in space that likely corresponds to the change in ice conditions. Yeah, the wrong point out there. Yeah, anyways, this is the thing that I think is super cool and I'm super excited about, to have this type of spatial resolution also over time, where we have this temporal data of this type of evolution, really opens a lot of doors for us to get into better process understanding of wave ice interactions and what's driving wave attenuation. Additionally, I showed earlier that we have the potential to invert this type of data to get at the ice thickness at the surface as well. So potentially coupling this with those observations of ice thickness is going to be critical for validating or calibrating models of waves in sea ice for use in modeling waves and associated processes in these regions. So we can also take advantage of that really incredible combined spatial and temporal resolution to understand how things are evolving over time. So this plot shows an example of that from, I think, about a day, where we have the time is on the x-axis, and then the y-axis is again this spatial slice along the cable. And the colors are indicating the attenuation rates. And so there's some obvious features that jump out. When we have these really high attenuation rates, we assume that those are associated with thicker ice. So thicker ice is going to have higher attenuation. It's going to damp the waves more dramatically on the surface. So from this data, we can see where we would expect thicker ice on the surface. We can also see changes in where the ice edge, indicated by the dashed white line, is located. So initially, there's some compaction of that ice edge. And then towards the end of this time period, we see that advancing offshore. So we're understanding how that ice is evolving over time and over space. And we can quantify aspects of that as well. So looking at this, this change over time, we can calculate using the change in location of the ice edge over those about 13 hours, the expected velocity of that ice edge convection. Following on some previous work, we expect that the radiation stress gradients at the ice edge can drive ice motion both along the ice edge, but also in the cross-shore direction. So we can calculate what we would expect based on linear wave theory, that ice edge compaction to be from the radiation stress gradients, which for this case would be about 0.1 meters per second. And that agrees pretty well with what we observed in this plot. And so this shortward velocity, in addition to likely some contributions from Stokes drift and maybe direct wind drift, are likely resulting in the convection of the ice edge into this higher concentration layer, where we're also getting this potentially thicker ice closer to the coast. This is taking a good start again. So this is a video that's really involved there. So, and I just wanted to end the summary of this section with this video showing this really high spatial resolution. And this is like a place where this type of method can really shine, where we have these fiber optic cables can measure wave ice attenuation with unprecedented spatial and temporal resolution. And this is especially important because the models are missing a lot of the interactions and feedbacks that are driving Arctic coastal changes. The signals that we see in this data can be used as proxies for ice evolution, especially during events where we have strong changes and rapid evolution in the signals. So the examples that we saw of that are the wave-driven advection, which we can estimate, and also spatial variation and attenuation, which can be related to the ice conditions. So those are some really cool applications of this for this Arctic region that I'm really interested in. Oh, one more slide on this. We are going to, so I mentioned that we're continuing to work on this. We, in the past, we just had this one wave buoy, which we used for calibration. This last year, we deployed 3 moorings through the ice in the spring and then recovered them from a ship in the early fall. And so we got a time series of those wave and water temperatures over that period. And so with this larger data set, we hope to explore better calibration methods for this to improve on that using machine learning and data science approaches, and to hopefully better understand also like what density of empirical calibration data you need to be able to use these cables for this type of work. So that's coming up for that work. I want to transition into talking a little bit also about some exciting applications of this for coastal zone work. So recently, I've been working with some collaborators at WHOI using a cable at the Martha's Vineyard Coastal Observatory to explore a lot of different potential applications for using seafloor cables with DAS in this type of mid-latitude region. So this is not a telecommunication cable. In this case, it's using this cable which goes out from a lab to an air-sea interaction tower. So it was installed for scientific purposes, but it's a very similar cable type. So we have about 8 kilometers total of cable. And in this experiment with collaborators Wenbo Wu and Jishao Shen, we're exploring, basically trying to understand all the different things that we might be able to use this cable for in the coastal ocean. So they're both seismologists, so they're really interested in a lot of those signals. And in this experiment, we're particularly interested in, I'm going to talk about these first 2 that we're exploring using this for. So they've been looking a little bit at using it for tides and also hopefully eventually understanding coastal groundwater levels. But we're working on exploring the ability to measure a lot of other things in this region as well. So potentially changes in bathymetry. Because we're measuring up to very high frequencies, these types of cables have also been used for observing and localizing marine mammals. I mentioned seismic acoustic signals. And then there's also just a lot of, like man-made noises that you can see. Actually, interestingly, from a recent deployment we had, they're installing this vineyard wind right offshore here. And they're currently doing pile driving, and it's very loud. You can really see it in the data. So also exploring how you can use these cables to monitor different ship traffic and construction noise and other acoustics in the ocean. So the data I'm going to present, just give little teasers of right now, is from one experiment that we had in 2022, but we just began another 2-month experiment here. So I have a lot of things I'm excited with this data, but I would be excited also to explore different directions that we might be able to use this data set, both that's existing and in future deployments for other applications. So one thing that my collaborators have been working on is exploring the ability to measure these long frequency, long period signals like tides in the coastal environment. So they're actually using here the onshore part of the cable and using a method called time-lapse seismology. And so the interesting thing here is that I think so far people have kind of largely assumed that you can't see really low frequency signals you need some variation and strain along the cable to be able to capture signals. But they've been applying this methodology where you can do basically cross correlation between different channels of the fiber and treat them kind of like one of them like an active source and see how that signal propagates to the other one. And so from the cross correlation of a bunch of different channels over time, you can see, so that pulls out these kind of low frequency signals. So this is showing the cross correlation matrix. So this is the time over the month of the experiment, and then arrival time is on the y-axis. And so this little zoomed in plot is showing a period during a storm. where they see these 12-hour signals, which correlate really well with the tidal frequency. So maybe it doesn't seem that cool to just like be able to pull out tides because we like know what those should be. But there's also some really interesting like variability on top of this, which we think is related to changes in the groundwater table level, potentially saltwater intrusion. So we're working on having more validation data to explore the ability to use this for these kind of like long-term changes in low frequency signals. Yeah, and of course, I'm interested again in using it to explore how we can measure the waves here. And so we've, similar to how we did in the Arctic, we're using an in situ sensor. Here we're using an ADCP to calibrate the data. The benefit here is that we actually have two different wave sensors. So we're using a different sensor for the calibration than we are for the validation. And so this is the calibrated DAS data in black compared to a wave lidar at the tower. And so in these time series, you can see that it compares pretty well. There's a little bit of an offset at this peak, but in general, it captures even this very big storm that we saw just before Christmas last year. Yeah, and the spectra also look pretty good. So this is spectra just from that point in time where it captures the peak pretty well. There's a little bit of a difference in the higher frequencies. So there's definitely more room to improve the methods for calibration here. But in general, it's doing really well at capturing both the spatial and temporal changes in the wave climate. Yeah, and so these are just correlation plots over 0.8 for both the wave height and the wave period, which is pretty good for a first try. Yeah, so there's a lot of potential applications for this type of data for understanding nearshore processes beyond just the waves as well. So Hannah Glover and Megan Wengrove at Oregon State University have been working as well on doing these types of empirical calibrations of the waves, but then also taking it a step further to drive a lot of really useful parameters of understanding what's happening near the coastline. So those are two examples from a paper that Hannah has in review right now that I just wanted to advertise because it's really exciting stuff where we can see on the top. So this is the wave reflection coefficient along this transect of cable that they deployed offshore the field research facility in Duck, North Carolina. And so you can see this, what this shading is indicating here is where there's a sandbar, and so they can see an increase in the reflection over the sandbar. So it's really cool to be able to capture that in that high resolution. And yeah, with just a little fiber optic cable. The bottom is showing also a method that they use to calculate the bathymetry. I think it's in the blue is there's two methods using the DAS, one using it as an array, one just as a single array, but they compare pretty well with the survey. And so, yeah, I think there's a lot of potential to use these seafloor pressure and wave signals to derive wave evolution, to understand nearshore and surfzone processes, and getting specifically at things like wave reflection and bathymetry, and hopefully also bathymetric changes over time. This is still all very new stuff, so there's a lot of room for improvement in the methods and also exploration of other potential ways to use these signals to do really cool and exciting things. Yeah, so this is my last summary slide. I think we'll have some good time for questions, but yeah, hopefully I have made the point to you that I think seafloor DAS is a really promising method for mapping coastal processes, particularly in highly spatially varying regions. So one example of this is Arctic coast, where there's a lot of variability in sea ice thickness, and we can use cables to explore wave attenuation, wave ice interaction processes, and to better understand the coastal exposure. But it can also be really useful in nearshore oceans for a lot of different applications, hopefully in understanding surface wave transformation and wave reflection, as well as eventually changes in bathymetry and how those different processes interact. Yeah, so happy to take any questions and hopefully talk about other applications that we might be able to explore with this type of data. Thanks.
Last questions. We'll start with one. So has anybody done anything with CODAR overlapping?
I don't know what CODAR is.
C-chip radar.
Oh yeah, okay. So I think there was an experiment that they did out in Oregon where they had a radar on the shore that they're comparing that to. And I know that Yeah, so they're comparing it
Because it
with
gives,
that.
CODAR has that spatial
Yeah,
result of wave characteristics. so
right.
like it's-
Yeah, so I think that's a really good thing to compare it to. And yeah, so one of the other things that they're exploring with that data set too is like also whether you can see like internal waves, which I think is a really interesting other application for it. Yeah, so that's something that Megan Wengrove's work that she's leading at Oregon State. Yeah. But definitely, yeah.
How long does it take to make a measurement? And can you synchronously measure all those points like at the same instant?
Yeah, that's the incredible thing. And that's like kind of the magic of the instruments and like the kind of, there's a lot of companies making these instruments that all have kind of their specific flavor in the way that they do that transformation and the processing or what's the word I'm looking for? Filtering, I guess. But yeah, so you can measure, hypothetically, you can measure all of up to 40 kilohertz on the instrument that we use. That I think that data gets a little bit, it just has problems like even saving it usually. But also it's not, yeah. So anyways, it can measure all of them synchronously. And I think that's one of the things that's really cool about it is having those coherent measurements along this long array. I mean, you can do that with like, strings of pressure sensors, but to be able to do it all in one instrument is like pretty.
And do you think detect ships passing over here?
Oh yeah, for sure. Yeah.
That'd be good.
Yeah. And that's one of the things that like we, have shown, like, I don't know if they've put out a paper on it, but you can definitely see it in the Arctic data as well as the data from the Coastal Observatory in Martha's Vineyard. The Arctic data, it's also kind of funny, like the drilling operation, they have like a hovercraft that they drive out to some of the oil platforms, and that is like incredibly noisy, like way more than a ship. You can see it across like the entire fiber. So those sorts of man-made signals are super clear and hard to miss because they're just really loud compared to everything else. So.
Has anybody tried to beamform the data from the big giant long aperture array?
You mean like to localize things or? Yeah, yeah, absolutely. I think that's probably what a lot of like people who are funding this for like kind of like defense applications, like that's what people are most interested in that direction. And that type of localization is similar to the kind of method that you use for marine mammals too, for localizing where they are. So yeah, that's definitely like yeah.
Yeah, so if you have, like you were talking about these other signals that you're picking up, whether it be from ships or whatever, or I mean, I can imagine like even seismic activity and stuff like that, imparting some strain on the cable. Is there ever any challenge like to actually be able to separate out the wave data from all these other, signals that might be also imparting a strain?
Yeah, I mean, I think a lot of it comes through filtering for the right frequencies. I mean, a lot of the different signals that we're talking about are fortunately like within different frequency bands, but there are things that overlap. And I think, so for example, that spectra that I showed where we had that high frequency peak, I mean, it's also, we have one hypothesis that it could be like a wave harmonic. So it could actually be related to the surface waves, but it could also be something completely different that happens to be within the same frequency band. So there are challenges with it. In general, things are like within, you can filter things to the frequency band that you're interested in so that there's processing ways to deal with that. But there may also be times when there's, for example, like the hovercraft just like puts noise through all the every frequency, every channel. And so that kind of makes things unretrievable. But like, other than those types of like extreme events, typically you can deal with it pretty well. Yeah.
For your experiment, did you have to install the sensors or work with a company to install them, or were they already on this cable and it was just convenient for you? And then of like the publicly known telecommunications cables, how common is it for them to have these sensors? Yeah,
well, so it's taking advantage of, so they're using the fiber optics in the cable anyways. So that's what this was already installed for the purpose of like sending internet. So all telecommunication cables have fiber optic in them. So, but the challenge is that not all of them have like extra fiber. So for this, at least for this specific instrument, we need what's called like a dark fiber. So there's no other signal that's using that specific fiber. I mean, there could be like, I don't know how many, up to how many, but there could be like a dozen fiber optic cable or fibers in the same cable, but we just need one of them to not have anything else on it. But there are, so the reason we're using this one is because all of these other like parts of it don't have dark fibers that we can use. So that's like the challenge in some of these environments, but like largely, I think they do install extra ones for like some redundancy, so. Yeah, so it's taking advantage of what they've already installed, so all we have to do is hook up our instrument, which is just like, kind of like the size of like which is like a server size, that on the shore side of that cable and just like plug it in. So it's, once they've like trenched and deployed the fiber, which is a huge process, very expensive, but worth it for them, the process to collect the data on our side is very easy. There's kind of different approaches though, like some are charging, some, I think because it's kind of new, some telecommunication cables are like charging a lot to do that, like huge leasing fees, but some are just kind of like, this is a cool new application, kind of have a good relationship with scientists and allowing it to happen for free. So there's a lot of variability in like the openness of different companies for that, but yeah.
Thanks, very nice talk. You just mentioned trenching, so usually the cables are within the sediments.
Yeah.
And you know, that's one of the, we are trying to work with that for seismic, seismology applications.
Yeah.
So the coupling between the ground and the cable is very important.
Yeah.
In your case, that would maybe be annoying relative to
Yeah.
signals from the ocean, I guess.
Yeah, we prefer to have it just on the surface, although you need it like a little bit buried because you don't want it like moving around.
Yeah, we have also problems with currents actually.
Yeah, but ideally it would just like be barely buried. But so here they hypothetically buried it 4 meters below the surface, although I'm not sure that's true because I don't know if you would have heard, but they actually had a big cut in the cable. The spring, the cable was like sliced by an ice keel like right in here, and they had to go like they had to like go pull it up and resplice it and with like divers and all this hoopla to get it like all the North Slope lost internet. So they do tend to trench them in the coastal region, which, yeah, so we are doing, so in this empirical calibration, like we kind of get around knowing exactly what that is by just calibrating it to what we know the waves are at the surface for a given time. Megan and has a paper that's in review doing like an analytical correction or analytical transfer from the strain to pressure, but a lot that really relies on knowing very precisely like details of the fiber itself, exactly how deep it's buried, exactly what that bed substrate is, and there's a lot of those things that are just really hard, if not impossible, to know for most applications. Yeah, I don't actually know if that answered your question, but yeah, so it's
Comment with respect to his question, there's no sensors really, the cable itself is the sensor.
yeah, the cable is the sensor.
That's what is
Yeah.
important, and that's a big advantage.
Yeah.
We have some difficulties to find telecommunication companies ready to actually let them use cables.
Yeah. I think they're becoming more open to it, especially if there's like monetary need for it. But I mean, I think, I don't know, I think for some of these applications too, I think there's an argument that it's worth also deploying some of our own scientific fibers. I mean, so I think like MVCO was obviously deployed for a different application of that for that coastal observatory, but that's a great cable to use. The experiment that Megan did at Duck, I mean, that wasn't left out for a terribly long time, but it showed that you can do these kind of like short deployments of fiber, like, you know, just kind of throw it in, let it self-bury over the course of a few days, and then you can use it for science over the course of a few months. So there's, yeah, definitely like the ideal is to be able to take advantage of the existing infrastructure because that's no additional, well, or at least minimal additional cost, but there's also ways to kind of deploy our own too, potentially.
Curious for the duct deployment then, so it was just deployed, was it recovered? Is it recoverable?
Yeah, I don't know. So I was not actually involved in that experiment. That was really work by Megan Wengrove and that Hannah Glover is analyzing too. I don't know if they recovered actually. It's a good question. It's like, it is a very small fiber. I mean, so it's possible they just left it out. And I know that it does kind of get buried within a matter of days, but I don't know what the like, yeah, I guess there's like there's downsides of like leaving that trash in the ocean. But I mean, I guess the telecommunication cables leave. If you look at the map of fibers across the ocean, there's a whole lot. So I guess it's a small impact of it. I don't know. I don't know if they removed it. I don't know how feasible that would be. It seems like it'd be hard.
But it obviously wasn't that expensive.
No.
I wonder if you could put 10 out and so you could get a long shot.
Yeah, I mean,
variability,
I think that would be really cool.
if they're cheap. But
Yeah.
I don't know how cheap it is.
I think it's relatively cheap. I mean, it depends on exactly how armored you want it to be, but like, I mean, they use fiber optic. I mean, they like run it all through towns. I mean, you know.
Or maybe the cost may be the cost of the instrument rather than the cost of fiber.
Right, yeah, but the instrument is on the shore side, so that has like, it's a much,
Yeah, but if you had 10 spread out along the coast,
Yeah.
either you have multiplex or you need 10.
yeah. Yeah, or you like do a, whatever, some other kind of clever zigzag,
Okay.
because you can measure, up to, kilometers of cable at the same time. So you can imagine lots of different deployment configurations that could give you lots of different information.
Time for one last question, if there's one.
Do you have any problems like georeferencing the cable? Do you have to have a really good idea of where the cable is?
Yeah, so ideally we do, but so this was actually cool. I think that I didn't really. So in this experiment, they deployed this cable and they kind of had like a rough idea, but they didn't have like great localization of it. But so they did an active source experiment as part of this like DAS experiment last year, where they had a bunch of like active sources at all these points and used that to localize the whole fiber. And I mean, I don't know what he said he thought the accuracy was, but like centimeters, like that's very good. So, and I think that you can do that with like, you can definitely do it with like an active source experiment, but you can also likely do that with like active sources like a ship where like you can see it along the whole fiber. So I think that ideally like you kind of go into it knowing where it is, but also there's ways to do it with the signal itself because of the spatial resolution ability to see signals along the whole fiber.
Thanks. Let's thank Maddie again.